Hey everybody, this is Mr. Woodward. In this video, we're going to look at some examples of objects that are experiencing forces at angles, but that are accelerating as a result of those forces. Let's jump in. In previous lessons, we looked at objects in static equilibrium. These were objects whose forces were balanced so that the net force was always zero. This meant that the sum of the forces in the horizontal direction was zero, which we could write as sum of forces x equals zero, and the sum of the forces in the vertical direction was zero, sum of the forces in the y is zero, okay? But now we're gonna look at something different. Now we will look at objects that are not in a state of equilibrium. These objects are accelerating, so their net force is non-zero. If their net force does not equal zero, then what does it equal? Well, Newton's second law tells us that the net force is always equal to mass times acceleration. That's always true. This means that for accelerating objects, the sum of the forces in each direction is the product of the mass and the acceleration in that direction, okay? So previously, we would say that the sum of the forces maybe in the x direction equaled the mass times the acceleration in the x. And since an object was in equilibrium, well, the acceleration in the x direction was zero. So the sum of the forces was equal to zero in the x direction. And for an object that was at rest, we said, well, the sum of the forces in the y would also be equal to mass times the acceleration in the y direction. But again, for an object that's at rest, it's not accelerating. So its acceleration is zero, which means that the sum of the forces in the y direction was also zero. Okay, and that is why this made sense and this made sense, right? Because the acceleration was zero. But now that the acceleration is not zero, we're going to use this for the x direction, this for the y direction. Okay, let's try a few examples of that. Number one, the painting on the right is hanging in an elevator, but the elevator is accelerating upwards. Okay. Not only does that mean that the acceleration is up, but the net force will also be directed upwards too. The painting has a mass of 3 kilograms. The tension in the leftmost rope is 7.2 newtons. So I'm going to call this 7.2. The middle rope, this tension is 16 newtons. And in the rightmost rope, it is also 16 newtons. Okay? Determine the acceleration of the painting. Well, as always, we're going to start by drawing a free body diagram. So here we go. Here's the painting. We've got the 3 tensions, and we have the force of gravity pulling down. Okay? That's going to be equal to the mass of the painting, which is 3 kilograms, times 9.8 meters per second squared. So this is going to be 29.4 newtons. I'm going to call this T1. I'm going to call this T2. I'm going to call this T3. T for tension. We know that this is 16 newtons. We know that this is also 16 newtons. We know that this is 7.2 newtons. And we have these angles. This angle here. Well, this angle is 40 degrees. So by geometry, this is an alternate interior angle. So that's also 40 degrees. This angle here was 70, so we know that this is also 70 degrees. So I can go ahead and label this 40 and this one as 70. All right, first, let's find the sum of the forces in the y direction. Okay. By the way, we know that the sum of the forces in the x direction is going to be equal to 0 because the object is accelerating upwards, right? It's not moving left or right. It's only moving up and down. In this case, just up. So the sum of the forces in the x is 0. We want to know what the sum of the forces in the y direction is. So let's use an expression for that. The sum of the forces in the y direction will be equal to the vertical component of each of the 4 forces that are acting on the painting, right? So T1's vertical component is going to be the force, the 7.2, times the sine of 40 degrees. T2's vertical component is just T2 itself, because T2 is a 100% vertical force. If you wanted to double check that, you could say T2 sine 90, which is just 1. So I'm going to leave that out. And then T3 times the sine of 70 degrees. That's a 7. Okay, those are the 3 upward forces, and then there is one downward force, which is the force of gravity. So I'm going to say plus the negative force of gravity on the painting. So here we go. 7.2 newtons times the sine of 40 plus 16 newtons plus 16 newtons times the sine of 70 degrees minus the weight, 29.4 newtons. And that is equal to 6.26 newtons. That's the net force in the vertical direction. Okay? Well, again, the goal is to find the acceleration of the painting. So step 2 is I'm going to set the sum of the forces in the y direction equal to the mass times that vertical acceleration, and then solve for vertical acceleration. Okay? So here we go. Sum of the forces in the y direction is 6.26 newtons. The mass is 3 kilograms. And then the vertical acceleration is the only unknown. So solving for that vertical acceleration, it's going to be 2.09 meters per second squared. And what's the direction? It's upward. Okay? Because, well, actually, it told us that in this in the problem statement up here, right? It said it was accelerating upwards. Okay, so that's how you can incorporate forces at angles along with Newton's second law to figure out an unknown acceleration in this case.